Knock, knock, it's Mr. Knock. All right, let's get into these notes. Ooh, we're starting Unit 2, and this is where we start getting into the real calculus. We start learning about all these things called derivatives and how they apply to our functions and all these properties. It's a lot of fun. You're going to have a great time, I promise. Okay, so today we're starting off by talking about average and instantaneous rate of change at a point. So there's a couple things we kind of got to go back and think about, right? Okay, so let me just go back way back when you learned algebra 1 skills, right? So in algebra 1 we started talking about lines, right? We'd graph a line and I would say, well, with this line we can write an equation, and we write the equation by calculating first where the y-intercept is. I don't really care about that though. What's more important is that we talked about the slope. You would find the slope by calculating what's the rise over the run, right? Rise over run, and you'd get a slope. Well, then at some point in pre-calculus or college algebra, maybe algebra 2 if you took algebra 2, you learned about average rate of change. We don't do a ton with it, but you used it. And the idea of average rate of change is that if I had a polynomial, so for example, you can see I like this picture here. Right here, they take this polynomial, and if I wanted to find the I can't really calculate rise over run of a curved line, right? We can only calculate rise over run on a straight line. So what we did is we would connect 2 points, make a straight line, and use that to approximate what the slope would be at that point, right? And we call this line, by the way, this is a definition that easily gets forgotten, so you might want to highlight that because that's a geometry definition. And I know that might have been a little while for some of you, at least 2 years for some of you. A secant line, by definition, is any line that crosses a curve twice. It doesn't come up a lot throughout the calculus school year, but it does come up sometimes. So I want to make sure you hear that word, you highlight it, and you make a mental note to remember that word. So basically, if we drew a secant line, right? So for example, let me actually come over here to the parabola. If I drew a secant line from here to here, that's going to create a line that we could find the slope of. Well, what would happen is if I got those points closer together and closer together, the slope would start getting more and more accurate to what's happening at that point, right? If I pick 2 points that are far away, right now I'm saying there's a positive slope here, but it goes up and then comes back down, so that's not a great estimate. But if I were to calculate the slope from 2 points really close together, it's a pretty good uh, approximation of what the slope is, which leads to what we're going to talk about today called the instantaneous slope. Instantaneous rate of change. The instantaneous rate of change is what would happen if I took those 2 points and I made the slope between them, right? And then I put those 2 points closer together, and then I put those 2 points closer together, and then I put those 2 points closer together to the point that I only get down to one singular point, taking the slope at one point. Well, you can't really do that because we can't do y2 minus y1 over x2 minus x1 using that formula, right? Which is where these definition of tangent line problems come from. So you can see right here, f is defined on the open interval. We're going to take the slope of the tangent line. Now that's what that's called too. If you don't remember from geometry, a line that only touches a curve one time is called the tangent line. So I've got a secant line and a tangent line. That was in that circles chapter in geometry. Okay, so if I want to find the slope, what we're going to use is these two formulas right here. The slope is when I take the limit as x approaches c, and you can see this is your slope formula, right? It's y2 minus y1 over x2 minus x1. It's just they're using an x and a c for our x values, right? So that's what they're doing, but you're taking the limit, you get closer to c. You're getting closer and closer and closer to being one singular point. And that leads us to this derivative function of f prime. This, by the way, is how we say derivative in short. So this is the derivative of f, but we just call it f prime. If you want to write that word somewhere, prime. That's what that little apostrophe means. So f prime, the derivative of f, is equal to the limit as h is getting closer to 0 of x plus h minus f of x over h. And that is how you calculate the derivative. The derivative, which we'll learn a little bit more of later, is the slope of the instantaneous point, right? If you were to put a tangent line at a single point, the slope of that tangent line is the derivative. That's what you got to really connect, is the derivative is slope of the tangent line. I don't know if that's written anywhere necessarily, but I'm gonna write it right here. Derivative is slope of tangent. I guess you could have written like the m tangent like we had up above. Okay, so let's actually try that here. I got this problem. It says differentiate f of x equals square root of x. What you're going to know, by the way, especially if you like ask any of your BC peers or go to tutoring, there is a much easier way to do this problem that I'm about to do, and that's okay. I want you to do it the long way for this set of notes. I really want you to practice the long way because you have to know how to do the long way as well. And then we're going to learn some shortcuts in the next unit, and it's going to like make this all make a lot more sense and make it so much quicker. But for now, though, I need you to use this formula right here. So we're going to write the limit as h approaches 0, okay? And then on top, they want us to put f of x plus h. So anywhere I see an x, I need to replace it with x plus h. So right here I got square root of x, so I'm going to rewrite it as square root of x plus h. Okay, then our formula has minus f of x. So I'm going to put minus, and then I'm going to write the function exactly how it is, square root of x. Okay, and then on the bottom, I've got h. Well, here's the problem. If you just plug in 0 right now, right? If you just plugged in 0, right here you plug in 0. X plus 0 is just x, so you'd have the square root of x minus the square root of x, which equals 0. And on the bottom, if you plug in 0, you get 0, and you have 0 over 0, which is an indeterminate limit, right? And we learned this back in unit 1, where we said, well, if there's indeterminate, we have to find ways to manipulate it. And you got that, right? This one, we know we're just going to multiply by the conjugate to make it a determined limit, an answer that actually exists. So I'm going to multiply the conjugate on top, which means I have to multiply the conjugate on the bottom. Okay, now remember we talked about this. Keep rewriting your limit notation until the actual plug-in step happens, which is frustrating, but we have to. Okay, so on top, I know that this is going to multiply here, and we're going to cancel out and just have x plus h. This is going to multiply here, and we're going to have x. So I have minus x. And then in the middle, we'd have x times x plus h and negative x times x plus h. So those will cancel out. It doesn't matter. That's what conjugates do for us. And on the bottom, I'm not going to do any multiplication. Don't try to distribute that h. It's just going to make the problem more complicated, and you're just going to have to factor it out later. So just leave it like that. Okay, you can start seeing some things that are happening here, right? Do you see how there's a positive x and a negative x? Those are going to cancel each other out. So now I could rewrite it, and you could definitely do this in less steps. I just like to show my work for my notes. But if you see right away what's about to happen to this h, you could jump to that step right now. Okay, x plus h plus the square root of x. You can see now there's an h on top and an h on the bottom, so these h's are going to cancel each other out. And remember, anytime you cancel everything on the top or everything on the bottom, there's still technically a 1 because it was 1 multiplied by h, right? 1h, so keep the 1 on top. So now I have the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x, and now I can substitute in 0. So I get 1 over, well, x plus 0 is x, and I have the square root of x here, right? And I plugged in 0 here. X plus 0 is x. Okay, and then if I add square root of x plus square root of x, I get 2 square roots of x. And that is the full derivative of square root of x. Again, that's what that is. That's the derivative, or it's the equation to calculate the slope of the tangent line. All right, well, that brings us to the end of first page, and I will see you in the next page where we can continue learning more about this.